Yeah, I think today is a geometric group series day. Okay, and we have access Professor Radhika Gupta from KFR and our former student Aishwarya who take this run the show today. And I just Radhika.
Thank you. Thank you for inviting me to speak here. This is my first time in Kerala and in KSOM. It's a beautiful campus. Nice. So let me just quickly tell you what my plan is. So I think the topic is introduction to Coxeter groups. So I'll make this table. These lectures will be talking about Coxeter groups from the perspective of geometric group theory. I don't know much about the representation theory or Lie theory aspect of it. And I think if you have questions how to connect those to what I say and how it relates to Lie theory, then I think Professor Safiri will be the correct person to ask, not me. Because I really don't know I think Tits and Coxeter were interested in these groups because they were interested in Lie algebras, classifying semi-simple Lie algebra. I think that's correct to say, but I don't know much about that aspect. I'm going to talk about from the perspective of geometric group theory and the my goal theorem. We'll see how much we can prove this would be that every Coxeter group acts properly discontinuously and go compactly on something called a CAD zero space. And the space has a name. In this setting, it's called the Davis complex. So in the morning session, like before lunch, my goal is to try to basically give you some idea of what this means. What does it mean for groups to act on spaces in this particular way, and why do I care about groups acting on spaces? And so this would be like introduction to geometric group theory, then spend some time telling you about what a CAD zero space is and why we might consider studying them, and why is it important, why is it useful to know if a group acts like this in a CAD zero space. And in the afternoon, actually, no, I think maybe I'm over ambitious, but this would be fun. This would be two, telling you about Coxeter groups in the second lecture. And third lecture would be trying to tell you about Davis complex. And fourth lecture, we'll try to see if we can get to the proof of this theory. And what are the references that I'm using? So the main reference here is Mike Davis's book. Geometry of, I think it's called Geometry of Coxeter group. And I specifically was looking at notes by Chris Cashin. So he wrote some notes based on this book for a course he taught, the notes on Coxeter groups. I think these are both excellent resources. Okay, so let's start with intro. Geometric group theory. So what is the philosophy for geometric group theory is basically you want to view, the first thing you want to do is view a group as a metric space. And then use the geometry of the space to say something about the group. Okay. And there are two kinds of geometries that I'm usually interested in. One is called delta hyperbolicity or Gromov hyperbolicity, which I guess today I will not talk about. And the other one is cap K geometry or cap zero geometry. Which we will talk about. So let's see how do I view a group as a metric space. So this is done by this construction called KD graph. So let G be a group. And let S be a generating set. And so I define KD graph of G with respect to this generating set is a graph with vertices. Vertices are basically the elements of G, and the edges are, I put an edge between G and GS wherever S is empty, my generating set. Okay. So let's do some examples. So G is Z, and I choose my generating set to be just the integer 1. So I have to draw some graph. What are the vertices of the graph? The vertices are all the elements of my group. So the elements of Z are all the integers. Then do I put an edge between them? If I can go from G to GS by, so S is just 1 for me. So I can go from 0 to 1 by adding 1. So I put an edge there. And basically I have an edge between adjacent integers. Okay. Now I can change my, this is not the only generating set. I could change my generating set and let it be 2 and 3. 2 and 3 will also give me all the integers, because 2 and 3 will give me 1, and then I have all the integers. So now what's the KD graph with respect to this generating set? So the vertices are still the same. I still have all the vertices. Now when do I put an edge? So now from 0, I put an edge going to 2 and an edge going to 3. From 1, there's an edge going to 3 and to 4, and then so on. And from 0, sorry, minus 2, I have to 0, and I have minus 3 to 0. I have some edges like this. So that's also an example of a KD graph. So KD graph does depend on the generating set that I choose. Okay, let's draw a couple more examples. G is Z squared, and my generating set is 1, 0 and 0, 1. Any guesses for what the KD graph might look like? Just the grid, right? The usual grid. It's the usual grid. Okay, what if I have P group on 2 generators? The way I've written it is already, I'm telling you what generating set is. This is maybe something we'll also go with some of you. So here, what are the vertices are the group elements. So I start with 1, then I have A, and I have B, right? But now I have to go from, okay, I can go from A to AB. That's my left. S is either A or B, or I can go to A squared. Here I can go to B squared or BA. So in Z square, what was happening? In Z square, I had 1, I had A, I had B, and then I had AB, and then BA. They were the same. So I got this square. But in the free group, there are no relations. Right? There are no relations, so they're not going to get linked up. They'll stay 2 separate points. And if you keep doing this basically at every yeah, so there will be so we A bar, A inverse. So if I can go from A inverse to 1 by just stacking on a A to it. Right? So if you keep doing this at every point, you'll see at every vertex, you'll have A going out, a A out, a B out, and an A coming in and a B coming in. So it will be your 4 regular tree. So the picture would be it will be a infinite 4 regular tree. Any questions so far? Let's do one more example and then we'll think about. Um. Yes,
So we choose a generative set is such that it does not contain both the element and its inverses. Rather than choosing that case, then multi-sets and multi-edges may not.
right. Yeah, if I chose A and A inverse both, then I would have these multi
So
edges.
I mean, are we assuming that basis will have to be the system just want to say?
Yes. Yeah, or my next example was going to address exactly that. That I'll make a convention that I don't want multi edges. Yeah, so my next example was this. Can it be a silly example? Not silly, but very small example. So this is just. Right, this is just this. Generated by S square is 1, right? And then I put S in my generating set. So what are my vertices? There are only 2 elements, 1 and S. So if I was going by that definition, I would put an edge. I can go from 1 to S by multiplying on the right, by like writing an S on the right. But I can also go from here to here by writing a like S on the right. So here I would have these multi edges, but my convention would be to not have these multi edges. Whenever I have these order 2 elements, I don't want to draw this multi edge. So for order 2 elements, convention. For order 2 elements. No multi edge. Yeah, so then let's also do this exercise for this group, dihedral group of order 3. So dihedral group of order 3 is the group of symmetries of triangle. And this is generated by a rotation and a reflection. Such that the rotation has order 3, the reflection has order 2, and SRS is something else. Okay, that's the dihedral group. I can write another presentation for this dihedral group where I have T and S, where T is now SR. If I pick, I'm just like rewriting a presentation, okay? T is SR. So then what do I have? I have, so S square is still 1, then B square turns out to be, because I can rewrite this thing as SR is 1, so T square is 1, and ST cube is 1. Okay. And then if you draw the Cayley graphs for these 2 presentations, they actually look very different. Yeah, let me just draw them. For the second presentation, we get this hexagon. 1 here, S, T. And for the other guy. Some picture. I'm actually interested in the second picture. But just to show you that they can look different. And how do I draw these KV graphs? Basically, I'm at identity, and then I decide how do I have some generators. So at identity, I can do S or T. Now, once I've done S, I can do S or T again. And then once I've done T, I can do S or T again, and then that's how you build your KV graph. Okay. And like Michael mentioned, I'm only drawing one edge. I'm not drawing these multi edges here. Okay, so far so good. Let's just quickly understand what's the group action. How is the group acting on these graphs? Okay. So in the first example, let's just look at the white line. How is Z acting on this? It's just translating it left and right. Okay. In the second example, means Z will still act by the same way, it's just that it will take one of these pink edges to another pink edge. The one which was at the gap of 2 will go to another one at gap of 2, so on. That's all. Z square, again, I know Z square is acting by translations. One element, this one moves it horizontally, the other one moves it vertically. You understand what the action is. In the free group case, we have not thought about this before, it can be slightly. It's simple, but can be confusing. So again, I want to say A is acting by, so what is A doing? It's taking identity here, then this to this, then this to this, and the backward direction. So A on this line, on this particular line, A is acting by translation. But then when A takes 1 to here, it takes this whole vertical branch and puts it here. So it's like, it's really moving this whole tree up. In Z square, it was moving this vertical line here. Here it's going to move even these, like this horizontal will go here, like that whole subtree will just like move to the next one, move to this one. And so, and what does B do? B is taking this vertically up. So I'm just telling you how the generators act. Of course, I need to understand how the whole group acts. But if I know how the generators act, then I know the whole action of the whole group. Right? Let's look at this example, or maybe even this example with just one edge. How is S acting on this? I like to think of S acting on this as a reflection. Right? And then I want to focus on this example. How are S and T acting in this? I've written everything correctly, I want to say. S is acting by reflection about this, and maybe I should use another color. I want to say S is acting by reflection about this, and T is acting by reflection about this. And it will be relevant later, but this angle is 5/3. Okay, so far what have we done? We have taken a group, a generating set. I've been drawing finitely generated groups or finite, like when I have a finite generating set. But you could, I mean, this picture I could draw even if I have an infinite. I could take my generating set to be the whole group. Every element in the group is part of my generating set. So then what would the KV graph look like? So let's say my generating set S contains all the elements of my group.
1 point.
1 point or? No, the vertices are all the elements of the group. So as long as the group is not trivial group, I will have lots of points.
So one center and
It's also loops will be there.
Loops will be there.
all will be all
All possible edges, exactly. It will be a complete graph on however many elements are there. That's also a Cayley graph. Okay, so I have my space and okay, if I want to convert these spaces into metric spaces, what would be your first, like what would you do? You have to convert a graph into a metric space.
Define the distances.
Define distances, and in a graph, what's the easiest way to define distances? Just give some length to each edge. Right? So, and then I might as well say each edge has length 1. That's how I do it. So I can think of these as metric graphs. Saying each edge has length 1. Okay, but now we have a problem. We have one group, it can have lots of generating sets. How do I mean, it doesn't feel like a good way of associating a space to my group. Because it seems like I could do anything. I could get a complete graph even, which is very different from a complete graph on there's very many points is very different from this line. So I want some handle on what these different spaces are like. Are they related to each other? Can I like put them in one box instead of really like saying these are different spaces that I have? Okay, so I'll make a definition using which we can say that all these Cayley graphs that you can define, they more or less look the same with some conditions. And because complete graph on Z many vertices does not look like the infinite line in any sensible way. Okay, so let's make our definition. Let x1 g1 and x2 g2 be two metric spaces. Map, and this needs not be continuous. So we often tend to think of continuous maps, not necessarily. I just specify not necessarily practically. It is a map from x1 to x2 for isometry. So for the lambda epsilon quasi isometric embedding. Okay, there exists lambda is 1, epsilon is 0, such that for every 2 points in x1, so I want to compare the distances in x1 and x2. Okay, the distance in x2 between fx and fy is I want to compare it to distance in x1 between x and y. So if I were to say by Lipschitz, right? If I were to say that this map is by Lipschitz, that would mean I just put this constant lambda like that. Right? That's called by Lipschitz. I'm just stretching the distances, stretching and shrinking them, but I have control over how much I do that. But when I'm doing quasi-isometry, I add this extra. I allow this extra first term, this epsilon. Okay. And we'll do an example to see what the but let me finish my definition. So this is a quasi-isometric embedding. And if in addition, there exists a constant C such that for every x2 in x2, there exists a x1 in x1 such that X2 is in the C neighborhood of f of X1. This is called the closely surjective. And if this happens, then f is called the quasi-isometry. And we say X1 and X2 are quasi-isometric. Okay. So what is the cartoon for, what's the picture for this? And basically I'm saying I have X1 and X2. I'm saying this map need not be surjective. Okay, this map need not be surjective, but if I have these f of X1s, if I take C neighborhood of the image, then I get the whole space. So it's coarsely surjective is the terminology we use. So the C neighborhood of the image is everything. The image might not be everything, but if I pattern it by this constant C, then I get everything. That's called coarsely surjective. So example, first example is a metric space is quasi-isometric to a point if and only if it has finite diameter. Let's think about this.
Mostly subjective, and then when is f called quasi-isometric?
Sorry, quasi-surjective plus, yeah, so this was in addition to, so I have a quasi-isometric embedding plus quasi-surjective, then I say it's a quasi-isometry.
So is quasi-isometry like a reflexive relation?
Yes. Yeah. Thank you. Yeah, I wasn't going to say that, but you can find a quasi-inverse if, yeah. If you're coarsely surjective, you do an example, then I wasn't going to like talk about it in detail, but I would say a simple example. But let's convince ourselves we understand. So if I have maybe one direction is easy. If I have a finite diameter space, and I can write a map F to a point, I just map everything to a point. Is that a quasi-isometry? Is that a quasi-isometric embedding? It's clearly surjective, not even coarsely surjective, it's surjective. What I have to see is, are the distances being changed by some bounded amount, by this linear function, is what I have to understand. So for this side of the inequality, like distances in x2, which is a point, this is just zero. This is just zero. So if I'm only concerned with this inequality, I could choose lambda to be 1 and epsilon to be 0. I don't have to do anything. It's a matter of this side. So what should I put lambda and epsilon so that this side becomes less than 0? Okay, it can. In general, yeah, it's greater than equal to 0. So here I'm asking you, what should epsilon, and so like in our example, this thing is 0, right? But this thing need not be 0 because x has some, I'm saying it has some finite diameter.
The diameter is fine. Take the diameter.
Take epsilon to be the diameter, lambda to be 1, epsilon to be the diameter, so that I make sure it's a negative number. That's it. So no matter what the diameter is, the diameter could be 1,000,000, it's still a finite number. So I'm allowed to take that. So from this perspective of quasi-isometric embedding or quasi-isometry, any finite diameter set is quasi-isometric to a point. And philosophically, you're supposed to think that if I look at any finite diameter set from far, it will look like a point. That's what Like even in, yeah. So quasi-isometry is if you squint your eyes and look at something from far, what does it look like? That's certainly what you should be thinking.
Metric space being quasi-isometric is same as finding some lambda and some epsilon.
Yes.
That's-
Yeah,
that's-
so I defined it, I defined, I defined F to be a lambda epsilon quasi-isometric embedding, if there is a lambda and epsilon like this, but if you forget you just want to say it's a quasi-isometric embedding, that means there is some lambda and some epsilon, such that this thing.
Oh, without coarsely surjective, this quasi-isometric embedding
Embedding, yeah.
actually go to a very small subset of X2.
That-
Without coarsely surjective, this quasi-isometric embedding need not be surjective on X2.
No, yeah,
Maybe very small.
it could,
inside
yeah,
So that embedding word is.
yeah, the word embedding is important there, yes. Like, yeah, when I'm defining quasi-isometry, I should say isometry is a quasi-isometry. Right? For isometry, I don't even need to bother with the lambda epsilon, these distances are just equal. So an isometry is an example of a quasi-isometry, and then isometric embedding, we understand. Like, real line quasi-isometric, sorry, real line isometrically sits inside R2, for instance. So yeah, this is a generalization of isometry. Okay, let's do another example. Yes,
It says C exists in addition to that.
yes.
So then the quasi-isometry embedding doesn't depend on that lambda epsilon?
So, no, I guess I'm defining two things. There's something called a quasi-isometric embedding. And the embedding is a quasi-isometry if you, in addition, have this coarsely surjective map. And you could choose the C will probably get, C. I should say that, it might depend on the lambda epsilon. Okay, so I think this is a more interesting example.
So this like C is independent of X2, is it?
Is it independent of X? That point X2?
Yeah, no. There's a C,
The space?
there's a universal C. So that for every X2 belong to X2, you must have C.
Yes. A shorter way of saying this would have been the C neighborhood of the image. Is it?
Yeah, that like the C may depend upon X2. No, what?
On the,
No, there is actually one specific C which works for all X2 belong to X2. Is that what you mean? Or?
yes, I don't,
Yeah,
yeah,
there you
yeah,
go.
it's independent of the point I choose it.
And also it's, these condition and that condition are independent, right? Those-
They are independent, yes.
So C is depend on lambda epsilon.
I think it can, because if you're like, I was saying your quasi-isometric embedding could map into like a really small portion of your,
Yeah.
you might be squishing the distances too much. So then when you take the C neighborhood, you might need to take a bigger C neighborhood.
But map is independent of what that lambda epsilon you're choosing on. Map is given and then you get a lambda epsilon out of it.
Yes, so what I'm saying is like the lambda epsilon you found out,
Yeah.
like you found some bounds, and using those bounds, those bounds tell you how much control you have over the image, right? Like how much, like let's say I stretch the distances by 100 times, or I squish the distances by 100 times. So that will tell me, that will give me some sense of how big a neighborhood I need to.
Okay, you might in the end be
You-
able to
yeah.
get C in terms of lambda epsilon.
Right. Right. It might be independent, but like. It
As
might-
condition it is independent, but you might be able to get C as a function.
As a
of-
function of lambda epsilon. Let's do this example. So now I'm giving Z a metric, be the induced metric on Z from R. Okay, then I claim that the map from the inclusion map from Z into R is a quasi-isometry. And okay, I can also have another map, let's call it that. by making two claims. Okay. Let's quickly think about this one so that we understand what quasi-isometry is. Little better. Okay, so the first one, when I have the inclusion map, Z sitting inside R. So let's first check. Which one should we check first? Is this, okay, let's check coarsely surjective. Is this map coarsely surjective? Right, the integers, if I take balls of radius 1 around integers, I get the whole real line. So it's coarsely surjective. Is this satisfying reasoning? I haven't changed the distances, right? With quasi-isometry, I'm allowed to change the distances by stretching and this additive constant. But here, I'm not even changing the distances. When it maps inside, the distance stays the same. So it's in fact an isometric embedding.
1, 0. 1, 0.
Exactly, yeah, 1, 0. So this map is a quasi-isometry. Let's just think about the second one. From R to Z. Like I didn't tell you what the map is, but can you find a map from R to Z, which is a quasi-isometry? Very sensible. What's a map? Like forget about quasi-isometry. What's a map to go from R to Z? Greatest integer or least integer. Pick your favorite, right? Pick your favorite one. So let's say I'm taking the greatest integer. Is it coarsely surjective? Yes. That I get all the integers. That part is easy. What's happening to the distances? I'm crushing distances now, but at most by 1. I could have two real numbers which were distance like very close to 1 apart, but I would have made them 0. And I do this now. So this is a quasi-isometry. So yeah, so what's the upshot of this? Integers in real line are, if you look at them from far, integers look like the real line. So I would say they are quasi-isometric. Any questions so far? Okay.
Okay, does it always happen like I have a map from x1 to x2, which is quadrate, or will I get some g from x2 to x1?
Yes. Yeah, this is the part I wasn't, it's even this is an equivalence relationship. If x1 is quasi-isometric to x2, if x2 is quasi-isometric to x3, then x1 x3 is also quasi-isometric. Yeah, so this is, you could try this as an exercise. I didn't put it as an exercise, but yeah, being quasi-isometric is a equivalence relationship. Sorry. Okay. Here is a lemma, which I'm going to set it up, but I leave this as an exercise for the exercise. Okay. So the lemma is that every finitely generated, and basically the point of the exercise would be going to realize why finitely generated is important, is a metric space. Where defined up to quasi-isometry.
Finitely generated.
Oh, sorry, every finitely generated group. So I'm going to, so this is what we wanted, right? I was saying we have so many Cayley graphs. How they make sense? So the next here would be that G is a finitely generated group, and I have S and S prime, two finite generating sets. then Cayley graph is with respect to G, sorry, S. And what's the metric here? The metric is every edge has length one. Yeah, we need this is the, like maybe I can even call it a proposition. And then I have lots of Cayley graphs. As long as I'm working with a finitely generated group, and if I take two finite generating sets, the two Cayley graphs will be quasi-isometric. They may not be the same, they will be quasi-isometric. Okay, so let me set this up for you. So I have G, my group, S, a finite generating set. I'm going to define a metric ds on G as follows. So ds of 1 comma G is going to be the word length. Word length of G with respect to S. So what is word length? We have to say that one. Word length is the length of the, you can always write a map from the free group on S to G. And then the word length is the length of the shortest representative in the free group for your and PS between G and H. That's the length of G inverse H. Yeah, so I guess I'm setting it up for you in the sense that I'm giving you a metric on the group, which is this metric. Okay, and then the exercise will be for you to show that now if I have ds and ds prime, then the group, the exercise is that group with ds is quasi-isometric to the group with the metric S prime. And when you do the proof, you'll see really why you need finite generation. These sets will be fine. Okay, so I'm going to leave this as an exercise.
Inclusion of a subspace inside a compact space. That seems to be a quasi-isometric.
Inclusion of if you take any space, like
So let's say S1 and S2 diameter, the equator or something. And that C can be easily found because of compactness.
right.
And that reality inclusion gives that inequality trivial.
No, G could be an infinite group.
Yeah, so if G were compact.
If G
and I-
were compact.
And I
yes.
took any inclusion
Yes,
of a subspace, that would be quasi-isometric.
sorry, I think any inclusion of a subspace, yes.
Would be quasi-isometric.
Boundedness is a better.
So from this
Exactly.
lens,
Not bounded or.
yes. From this perspective, here's another comment, this word length, this metric on the group that I'm defining with respect to S, it's exactly the metric on this Cayley graph, right? With respect to S. So I can think of the group with this metric is really just the Cayley graph as a metric space. That's what I meant by thinking of group as our space. And because of this proposition, it doesn't matter which generating set I choose. And because of this first example, if I have a finite group, so this is called coarse geometry, like, or whatever I'm talking about is called coarse geometry because somehow it's blind to any finite group. Which if you work in finite groups, you will be very unhappy because finite groups can be very interesting and rich. But somehow this theory is built to forget about finite phenomena. Right? Because if I have a finite group, its Cayley graph will have some finite diameter, and then I was saying it's quasi-isometric to a point. So this theory is just like going to forget about finite groups. In that sense. Okay, so keep this as an exercise for you. Think about. Let's let's go back to, we try to understand how groups act on these K graphs, but let me make a few definitions about actions. So basically now I'm interested in thinking about what the isometries coming from group actions. Okay. So if I have a group acting on a space, some topological space, the action is called co-compact. If there exists a compact subspace in X, such that G dot K is all of X. Okay. The action is free if it's free then for every X and X and for every G dot X is not X. Okay, so no point is fixed by anything. If I have a metric space, then G acts by isometries. I won't like this, but I just want to. Okay, that's why isometries is the distance between. XY is the distance between GX. dy for every G. And then, if I have, so I say this action on some topological space is properly discontinuous. Okay. For every compact subspace of X, the number of elements of G that don't move K off of itself is finite. Example. That's it. If I have a metric space. And if I look at this universal covered, so we have this universal covered. This I could have said topological spaces. Fine here. Then the fundamental group of X. So suppose it's non-trivial. The fundamental group acts on the universal covered by deck transformations. And if you remember your algebraic topology, deck transformations are exactly, they are properly discontinuous actions, right? Properly discontinuous. And if X was compact, then I could say it's also a co-compact action. What's an example of a not properly discontinuous action? So let's say this is my space. I have an infinite star. Infinite star. And Z is acting on it by just rotating. So it's an infinite star, it's a Z. Let's say there are Z many rays coming out. So I claim this action is not properly discontinuous. Because this whole group Z is fixing this point. So if this was my compact set, the number of elements G which are taking it to itself, like have not trivial intersection, here it's the same thing, it's not finite. This is not a proper action, it's not a proper discontinuous action. And then maybe exercise. values, like if you have a group G finitely generated, then G acts on the Cayley graph with respect to any generating set properly and program. So maybe you can think about this.
What is the action in that star example?
In this star example, the action is Z is acting by just like, so this was my array R1, R2, R3, R4. It's just taking R1 to R2, R2 to R3. And I'm assuming I have Z many things here.
You have infinitely many rays and still you can do this. I mean, is this well defined?
Why not?
Oh, because when you have infinite rays, the next one you can't see.
No.
No, I'm just saying, like, my rays are, it's countably, it's like countably infinite. Yes, like my rays are indexed by integers. Well, it's a natural number, yeah. Yeah. And then I'm just like saying, go to the next one. Okay, so why am I harping about these actions? Because there is this thing called fundamental theorem of geometric group theory, or Milnor-Schwarz lemma. So Milnor-Schwarz lemma tells you exactly if you have nice group actions, then you can say you can get some kind of nice Gaussian. So let's start with a proper geodesic matrix space. And let's say I have a group which is acting on this space properly co-compactly by isometries. So properly discontinuously, co-compactly, and by isometries. Then, just by knowing this much, first you can conclude that G is finitely generated, which is already quite nice. And for any point in the space, the orbit map is a quasi-isometry. The orbit map G2X This is saying if you have a nice action. So this is often called a geometric action. Then you can conclude that the group is finitely generated, and basically the group and the space are very close to each other from this quasi-isometry perspective. So you can think that Cayley graph of G, if you really want to very concretely think about a space associated to G, Cayley graph of G, any Cayley graph of G and X look similar. If you're wearing this classes which only see quasi-isometries. Okay, so what's an example?
Excuse me, what is the definition of geodesic matrix space?
Between
No, X is a proper.
any 2 points, there is a geodesic.
Oh,
I think here I wrote all the wrong assumptions, but I think you have a lens space, then also you can do this.
so what exactly is the definition? Because any 2 points, there's
It's geodesic.
it's just connected basically.
Shortest.
Yeah, just being connected does not ensure you are geodesic.
Shortest path may not exist.
Right. Like if I take R2 and remove origin. Yeah. Yes, the upshot of this thing is that if you want to know something about the group, if you want to know something about the group, and if you can actually find a space like this, then using the space, you can get some information about the group. So sometimes Cayley graphs are not always the best spaces to look at. even though this theorem is saying this space looks like the Cayley graph, but somehow Cayley graphs are not necessarily the easiest to understand. For instance, if I take the fundamental group, or yes, so simple example, in this one you do understand. If I take fundamental group of the torus, that's Z squared, and Z squared does act geometrically on R2, right? By that translation action. So, but here, okay, I'm not gaining that much out of. The Cayley graph is the grid, but it is acting on R2 by this geometric action. But for instance, if I take the fundamental group of a genus 2 surface, okay, this acts on, so if you, I'm not introducing hyperbolic geometry, but if you've seen it, then this is for you. Then this group is acting by direct transformation, right, on the hyperbolic plane, on H2. And this theorem is telling me the Cayley graph of this thing should basically force it's quasi-isometric to this guy. But the Cayley graph is some graph, some complicated graph. But H2 I really understand. The hyperbolic space, like a lot is known about that. Cayley graph might be like Cayley graph would be like a bunch of octagons glued together and tied in the plane. But the space H2 itself is much nicer than saying, like, look at the Cayley graph, for instance. And in fact, this might feel weird, but if I take any genus G surface, it also acts on H2 geometrically, right? Sorry. Any closed genus G surface acts geometrically. Its universal cover is the hyperbolic plane. So it's acting properly discontinuously compactly by isometries on H2. So any of those groups is quasi-isometric to H2. So these two surface groups are quasi-isometric. These are very different groups. They are nowhere close to being isomorphic or anything. But again, from the lens of this coarse geometry or quasi-isometry, they're somehow the same. Because I'm thinking, oh, they both act by direct transformations on H2. So I just need to understand H2 to say something about those in some sense. So they are quasi-isometric to each other.
What are we referring as nice green H2?
Nice meaning what? I completely understand its geometry, right? Like I know how to draw geodesics between 2 points. I understand its boundary. I know its classification of isometries. I know they're elliptic, parabolic, or hyperbolic. And I can really write down what they look like. So
It is well understood.
yeah, that's what I need to say.
What is a proper geodesic metric space?
So proper means closed balls are compact, and geodesic metric space meaning any 2 points are connected by a geodesic. Okay. Okay, then there are some exercises which I will now, but maybe I'll write it. I think I'm going much slower than I thought, but that's okay. So here is another theme. P group on 2 generators is quasi-isometric to any P group. We can think about this. Right, so why do we, okay, so one more thing about why we care about quasi-isometries. Okay, so what do I get by knowing that 2 groups are quasi-isometric, right? If they're isomorphic, then I often say isomorphic, they're really the same group, so I know a lot about the 2 groups. But what do I get if I know they're quasi-isometric? So I'll say some words, but I'm not defining these things. If G is quasi-isometric to G prime, then they have same number of ends. So just to give you a picture, what is an end? You look at a Cayley graph and you remove a compact set, and you keep removing bigger and bigger compact sets. So you want to know how many ends are there at infinity. So if I take the line, if I take the line for Z, If I remove a compact set, I get two components. And no matter how big a compact set I remove, I'll always have these 2 points at infinity. If I do it for z squared or KV graph of z squared, if I remove a compact set, if I remove a ball from R2, I have one connected piece. No matter how big a ball you remove, you'll always have one connected piece. So I would say it has one end. And quasi-isometry, basically how many ends you have is invariant under quasi-isometry. And then you will ask, like, why do I care about ends? You care about ends because there's a theorem by Stallings which tells you that if a group has more than, let's say, at least 2 ends, then somehow it decomposes into smaller groups. Either as a free product or something called free product with amalgamation. And that you really, if your goal is to understand a group, if somebody hands you a group, like you have it in your hand and you're like, what do I do with it? Like, how do I make sure I understand it, right? If you have a Rubik's Cube, you will start turning it around. If I have a group, if I can chop it up into smaller pieces, I would really feel like, okay, now I have to understand the smaller piece. So ends are related to telling you how a group can be split into smaller pieces.
That many.
Yeah, it's something called field product with amalgamation or graph of groups, if you've got these words. Another thing is something called growth is a QI invariant. What is growth? You look at the Cayley graph, you look at a ball of radius r and count how many elements are there. So it can either be polynomial or exponential, and 2 groups are quasi-isometric. Whether it's exponential or not doesn't change. For instance, sorry, I'm going very fast because this is irrelevant to what's coming next, but good to know. Then there's something called Gromov hypothesis. This is really, if I know that a group is Gromov hyperbolic, I can really say a lot from that. I can say it's finitely generated, finitely presented, it has to solve it with isomorphism problem. If I knew the group is 2 groups are hyperbolic, I can tell whether they are isomorphic or not. In general, there is no algorithm to tell whether things are isomorphic or not. For hyperbolic groups are like they are the hero or the heroine of geometric group theory. So, good thing that it's invariant under quasi-isometry. Okay, let's see. Any questions?
Different polynomial growths are not quasi-isometric.
Actually, let's see. Other degrees. I don't. Actually, I don't know. I don't remember it, but the degrees have to be the same one. I don't remember such.
These implications are all one way.
Say that again?
These implications are all one way.
Yeah. Yeah, I don't know about the.
They can't.
Yeah, that's a much harder question. Yeah, if I give you 2 groups, using these you can tell whether they are not, if they are not quasi. But to prove that they are quasi-isometric, it's much harder. Usually people will pick a small, I shouldn't say small, people will pick a subclass of groups. And then they will like work in that class and try to say, if I pick 2 groups that belong to this class, then maybe I can say that they are quasi-isometric or not.
Sorry, these are all finitely generated groups.
Yeah, I'm only so I care about finitely generated groups because KV graphs are quasi-isometric only if you have finite generation. Yeah, you know infinite generation, then some of this breaks down. So maybe what we'll do is let me introduce this CAD0 geometry, and then the next lecture we'll start by doing some exercises. These for half the time. Then you can also do exercises on CAD. Again, just like before I start saying this, so this cat K geometry, so the word cat stands for Cartan, Alexandrov and Tokonokov. They were all basically, they were parallelly sort of working on this kind of stuff. And this is to generalize or maybe like think more combinatorially about Riemannian manifolds of constant curvature in some sense. It's like a Riemannian manifolds of constant curvature. You want to generalize that notion and make it more combinatorial. That's the one. So for any real number k, and this is called my model space NKM, which is the unique complete simply connected Riemannian n-dimensional Riemannian manifold of constant sectional curvature. Okay. Equal to k. Here it's, you don't need to know what's the definition of sectional curvature for today. Basically what we need to know is that this model space of constant curvature -1 is hyperbolic space. Constant curvature 0, that's the Euclidean space. And constant curvature 1, that's the n space. Okay, and then I'm not going to talk about hyperbolic space in these talks, because that's a whole different thing. And if you want curvature k, usually you get curvature k just by scaling these spaces by something. It looks like if you have a sphere of radius 1, it has curvature 1, but if you make it smaller, it gets more curvature, bigger. Okay. Let's do this exercise together. And you wonder, okay, this is a proposition and it's black box because I don't want to do this. That there exists a unique Euler set between any 2 points x not equal to y in this space if the distance between x and y is less than something called the diameter. So dk is the diameter and it's infinity if k is less than or equal to 0, and it's pi over the k if k is greater than or equal to. Sorry, I'm saying there exists a unique, I want to say there exists a unique geodesic between any 2 points in these domains. Let's just think of these spaces, okay? That's true in Euclidean space, that's true in hyperbolic space. On the 2 sphere, let's just think of the 2, or even the 1 sphere, the circle. On the circle, there's a unique geodesic as long as the 2 points are not antipodal. Right? Because if they're antipodal, then the distance is pi between them and I can draw 2 of them. So that's why I just need this extra dimension. That's all. Okay, so let's do this lemma together. Let x be geodesic metric space. Consider a geodesic triangle delta Lx. Then there exists a unique geodesic triangle delta prime in in the 2-dimensional model space, it's same side lengths. Why don't you think about? I just think about k equals to 0 first. Maybe I just give you 1 minute to think. This is just like high school geometry, at least to get an idea. And I'm only comparing it to this infinity. So k equals to 2, meaning I just want, if I give you in x, if I give you a geodesic triangle with side lengths AB, let's say D1, D2, D3, this is in x. I'm saying that in E2, I can make a triangle with the same. There exists a unique triangle. So this proposition is telling me, this proposition is just telling me there's a unique geodesic between any 2 points in E2, in the 2-dimensional. But I want a triangle now. I have 3 points, not those.
The 3 points are fixed.
No. I just given you a triangle. I have my secret metric space, a secret geodesic metric space, and I have a geodesic triangle, and I've told you it's 3 lengths, D1, D2, D3. So they need to satisfy triangle inequality. That's true in any geodesic metric space, right? The sides have to satisfy triangle inequalities. And I'm asking you, if I give you these 3 numbers, which I know there is a geodesic triangle in some space, can you make a geodesic triangle in Euclidean space with those same 3 side lengths? Are you guaranteed that a triangle will exist?
No, can you repeat once more? Can you?
So let's say I give you I have my secret metric space, and I know I have a triangle, geodesic triangle with side lengths D1, D2, D3.
Yeah.
And I give you these 3 numbers. I tell you they satisfy triangle inequality because there's already a triangle in my space. I'm asking you in E2, can you draw a triangle with these 3 side lengths?
Okay. It's the same D1, D2, D3.
Same D1, D2, D3.
Okay.
So I'm giving you these 3 numbers and I'm telling you they satisfy triangle inequality. Each permutation satisfies triangle inequality. I'm asking you, can you draw the triangle in Euclidean space? Are you guaranteed that the triangle will exist?
And there is a unique one.
First is, can you find one, and then we'll worry about unique. How will you start building if you just had to start doing something? You draw one side. One side, of course, I can do, that's what you were saying, I have 2 points. So I don't know whether I have this, but I can, let's call this PQR. So I have my point P prime and Q prime. Of course, I can find 2 points like this. Fine. I can find R prime with D3 also. I mean, I can draw some lines. The question is, what about this guy?
Okay.
Yeah, so your intuition is just like continuously, at some point I should be able to get D2. Right? Because if what are the extreme pictures? The extreme pictures are that D2 is here and D1 is here. Sorry, D3. So what's left is D1 minus D3. And the other extreme picture is I have D1 here and D3 here. So the extreme is D1 plus D3. And I know D2 lives between D1 plus D3 and D1 minus D3 by triangle inequality. And the intuition is that if I'm here, if I hinge at this point, I can continuously rotate from D1 minus D3 to D1 plus D3. At some point I'll hit D2. And if you want to be, you can really write down, if this angle is theta, you can just apply cosine law to see that this side varies continuously with this.
For the Euclidean case, you don't even need geodesic matrix. You need 3 numbers which satisfy triangle inequality.
Yeah. I just wanted the triangle inequality. Okay. Again, I don't want to talk about hyperbolic, but if I were to do this in the sphere, Let me leave that as an exercise. Okay,
What about the uniqueness? What do you mean by uniqueness?
by uniqueness, so there will be, yeah, so when I'm doing this continuous, okay, I didn't think through properly, but I think there will be only one
One
D2, like, it's not like you'll have,
More than one between the
Huh.
three.
because this function would be like, this side is equal to cosine theta plus blah, blah, blah. So it's a 1-to-1.
There is at least one other, right? We can access, like, on the line, they are.
One up to unique up to something.
Yeah, I guess I have to see unique up to something, that's true, that's true, yeah. And then when you do it for, okay, so this was fine, exercises, try this for S2, and then you will really see that you will need to put some more conditions. So I wanted to find those conditions. Like this condition. Basically, whenever you're on a sphere, you always have to worry about geodesics not being unique, the distance between the points is 5. So you always want to say that things are less than 5 apart or something. So, okay, leaving this as an exercise, because I want to define what it means to be cat zero. So, geodesic metric space X is called cat K if for every geodesic triangle delta in X and the corresponding. So this thing is called a comparison triangle. This guy is called a comparison triangle. And the corresponding comparison triangle in yeah, so we were only doing it for k equals to 0 and k equals to 1, but you can imagine you can do it for any k. So I have the comparison triangle in this thing. It's called cat k for every geodesic triangle and corresponding the following now. So I have my cat x. I have my model space. This should be V1, V2, V1 prime, V2 prime, V3 prime, they're the same, V1, V2, V3, and the lemma tells me I can draw this triangle with the same measurements. Right? So what is the condition? I say this space is cat K if I take 2 points P and Q. If I take 2 points P and Q, if I take P and I look at P prime such that these orange lengths are the same. Okay, and then I take Q and Q prime such that these pink lengths are the same. Then I want this green. Wow, this is I want this green distance in my space to be at most as much as this one. So I want triangles in my space to be thinner than, they cannot be fatter than in the model space. So slogan is triangles are at most as fat as in model space. So for instance, I would say And the n sphere is cat one, Euclidean n space is cat zero, and hyperbolic n space is cat minus one. But for instance, I can also say that Euclidean, let's just say E2. E2 is, I can say it's cat one.
So in this definition, where does this actually K into the picture?
K is this model space. You're comparing your triangle to a triangle in the space with curvature K.
Yeah, but it is actually pretty close to length here and then.
Sorry, what's your question?
No, I mean just oh, you compare it to this. Okay.
Like the curvature will determine, like I think the difference between these lines.
Okay.
Like for instance, if I have to compare, so if I'm saying, so I'm calling it let's call it a claim. Maybe first let's see. E2 is this is E2. E2 is cat zero. That claim is fine, right? What do I want? I have my space E2. I have to compare it to M0. I have to compare, I have a Euclidean triangle here and a Euclidean triangle here. So of course, like the same thing. So of course it is cat zero, but I'm claiming E2 is even cat one. Why is it cat one? Because I have my Euclidean triangle, right? If I compare it to a spherical triangle, so basically I'm drawing a triangle in the sphere. Actually, I don't know what it looks like, but I'm comparing it to some triangle in the sphere. Yeah, so I left that as an exercise. For sphere, you have to check some conditions, but suppose there is a triangle in the sphere, then in the sphere, the triangles are fatter. Right? The triangle becomes fat in the sphere. So this triangle is no more fat than the spherical triangle. It's thinner than the spherical triangle, so I would say it's cat one.
No.
Yeah, so that's the thing which I omitted in this statement. When you're comparing it to, like for cat one, you can only compare triangles which you need to say like d1 plus d2 plus d3 is strictly less than 2 pi. Because even if you were on the equator, you could draw a geodesic triangle, but then the uniqueness fails. Yeah. So that's correct. I can't do this for any triangle. I have to, the definition has to, yeah, when K is positive, you have to really, these triangles only exist under certain conditions.
Then K will be depending on the triangle. You are taking the curvature at K. Let's say for different triangle, different case.
No. K is fixed. K is fixed. And I'm saying if for every triangle you can, K is fixed. And for every triangle in my space, look at the comparison triangle, which exists by the first lemma, and then compare those two triangles. Yeah, K is fixed.
So then you cannot really compare triangles in E2 with triangles in sphere. They have different curvature.
Actually, that's because yeah, maybe I shouldn't do that. You're right. Because I don't have a comparison triangle for every geodesic triangle. Yeah. Then I think the definition should be I didn't write it properly. The definition should be only for the ones you can compare. Compare it for everything you can compare.
The curvature K have to come. Right now it is not there in the definition.
No, it's there in the definition, right?
No, M2K is there, but how are you going to compare these two triangles? Whether or not there
Nobody-
exists a triangle.
Probably in the
That
definition.
has to come from this level. And I was claiming that you can always draw a triangle in M2K for any K with the same side lengths. Then these green lengths you are supposed to measure. Where am I measuring this green length? In the model space. The model space is definitely playing a role.
So ma'am,
Yeah.
you see metric space. And Quasi isometrically embedding,
Can you ask your question again?
even any geodesic matrices, can I quasi isometrically embedding? Comparison, it means I have to see this space in space, like trying to compare this space with my model space and
It's not,
in the.
no, it's not always clear whether you can put the whole space in.
Okay.
This comparison, I'm not putting the whole space in there.
At
I'm
least the
just putting
triangle,
triangle type.
some portion so that we can compare that triangle in our X, the triangle in our space X with the triangle in the model space.
Right. I don't need to put the space in there.
Not-
It's just these three sides. I'm not even saying the interior, I have to put it in there. Don't think of it as a filled-in triangle. Just think of it as the three sides, and I'm just saying I can draw those three sides in a model space. And the interior here is whatever it is, it lets me measure this screen. And here the interior is whatever it is, like on that model space. So like this is all sitting inside. This is all sitting inside model space. So in that model space, I can measure the screen distance.
Now, in the model space, that tree portion, that is unique throughout the space, right? Means if I give you D1, D2, D3, there won't be two triangles in the model space with different green. All the green, in that sense, it is unique there in the model space.
Yes. In the model space, there is a unique geodesic between any 2 points. So between P prime and Q prime, there is that geodesic. Now, maybe we should stop, then we can come back and do some exercises and we can ask more questions.
We don't require, this is fine, right? E2 is cat 1.
I think it's fine. You have to be careful which triangles you can compare is the question. I can't compare
Why?
every
Because you
triangle.
have geodesic.
This triangle was very big. And I tried to put it in, if these lengths are bigger than 5.
Yeah, then
These
you have
lengths are
some,
bigger than 5, then I cannot put it in the piece.
only that restraint is
So that restriction is, that's why, I mean, the objection was.
less than the
fair.
diameter of the.
We are also considering general. Because I was thinking of a silly example, like let's say my space itself is just a triangle.
Yeah,
And
Yeah.
it's too big of a triangle, then you cannot even compare any triangle itself. So then we have to consider only degenerate triangles.
okay, let me check, yeah, I think I'm confusing myself with this thing, let me check and get back to you in, like in the next.
No, but
session.
it won't be a geodesic, it won't be a geodesic.
So my space.
Only
itself
one
is-
triangle.
Space is just a graph.
Yeah,
Just a
yeah,
graph.
but if you take a vertex in between one side and another vertex in another side, the length is. And you give the length as the shortest length, then but here you have the geodesic is coming through this.
So actually it will not be,
will
because
not be a
in your
geodesic.
graph, you have to go along the sides. But when you put it in a model space, there will be that third side, and the third side is always smaller than the sum of the other two.
So it's not a geodesic.
So like one exercise is proving that a tree, if you take any tree, infinite or finite, it's cat K for any K. Maybe we can come back and think about that. That might help. That might help you work with this definition. Okay, thank you. Whatever the big thing. Yeah.
अच्छा कोणत्याही केससाठी there will exist geodesic comparison triangle.
Like I was saying, if this was a tree.
Also not there. Geometry.
It's a good food.
आणि इथून काय की why are you not taking?
Yeah, so like, part of what I want to do is architect. I mean, right now, I'm really talking about these modern spaces, but I think.
About the future.
I think our solution is like about them being captive. Yes,
Then of course, there are lots of.
yeah, so actually, that's like one. People who are interested in CAMZero, consider groups from this perspective are a good example because it gives you lots of spaces to.
Yeah, I didn't want to like disrupt you, so. But let us divide some particular thing that. I can talk about. But that's.
Yeah,
I mean, you know, I think, maybe it's a matter of perhaps already at first we just clarified that. If things are like this finite, it is not really very relevant,
Mm.
right? Because, you know, the definition you had from the. The maximum length between the maximum metric in X is finite. You can always take that C to be greater than that. And you put it,
right, right,
But anyway, that case is 40.
right.
If it is finite, then you can take the whole group, then you know, this, your maximum length will be one. And the corresponding graph is like this.
Exactly.
Yeah, but your next people get it bored. It is bored from the same. I think you'll know that.
Yeah,
I think, he will be available there, I hope. Okay, so let's go there.
you have a question?